Hello, everyone. My name is Alex Garcia. I am the creator of sqlite-vec. I am a software engineer based out of Los Angeles. Today, I'll be talking about sqlite-vec. It is a SQLite extension for vector search. I'll be talking a little bit about the extension itself, how to use it, how it works, also about like what vector search is and embeddings, and a little bit of background of like choosing an embeddings model and all the different cool features of sqlite-vec. And towards the end, I'll talk a little bit about how sqlite-vec works under the hood, whether that's about SQLite extensions or kind of how the internal shadow tables are structured within SQLite-vec that allows it to do the fast vector search that it does, and just a little bit more about like the SQLite extension ecosystem in general, as well as like other tools that you could use to play with SQLite a lot. So I'll be going through this presentation. I dropped a link to the slides in the Discord chat for this. Feel free to ask questions during the presentation. If it makes sense for me to answer, I'll pipe in an answer. Otherwise, at the very end, I'll try to answer all your questions and then kind of go through a little bit more. So it should be fun. Again, links are in the slides. Feel free to throw out questions anytime you want. I am recording this on my end, and I'll be posting it to YouTube or send it over to you all, so that way you can share with your friends or coworkers or whatever. So a little bit of background about me. Let me get this into a nice slideshow. Perfect. A little bit about me. I'm based out of Los Angeles here in California. I am a freelancer or contractor, I guess. I do a lot of short-time gigs between different places, so I'm not like a full-time in any one specific place. I guess context, I went to school in UC San Diego down here in sunny Southern California. Now I live up here back home in Los Angeles. I used to work in, big tech. So I was at Facebook for a little bit right after I graduated college. Decided I want to do some freelancing, kind of work in different places. My main thing right now is that I am working on Dataset Cloud with Simon Willison. If you've never heard of Dataset, actually I could take a look at it. Dataset is an open source project, also SQLite based, where you can kind of have a UI to explore a SQLite database. And you could have maps and visualizations and custom SQL queries that have links so you can share with coworkers and all. Dataset Cloud is going to be a hosted version of that, a paid version. It's open source. You could run it yourself, or you could use Dataset Cloud to kind of get started a little bit quicker or work with teammates and all. I've been working with that with Simon for a little bit, sponsored by Fly.io. And I also do a lot of open source stuff. So sqlite-vec is a project that has corporate sponsors, which I deeply appreciate. Mozilla AI is the biggest one. They're sponsoring a bunch of different like AI open source related projects, and sqlite-vec is one of them, which I'm very proud about, as well as a few other corporate sponsors that I have for sqlite-vec. So that's kind of what I do day to day for to make money at the end of the day, kind of contracting stuff and a few open source projects which I deeply appreciate. If you want to check out my website, alexgarcia.xyz, if you want to follow me on Blue Sky or Twitter or wherever else. Or check out my GitHub and all. Feel free to connect with me there. I also stay in this Discord server. If you have any questions, happy to answer any questions about sqlite-vec or SQLite extensions if you have, if that ever comes up. So it's kind of a little bit of background about me. And again, today talking about sqlite-vec. It is a SQLite extension for vector search. Definitely check it out on GitHub. There's a link to it right there. There's a documentation site that's still a little bit incomplete, but you can check that out as well. And that's what we're going to be mainly going to be talking about today. It's specifically this vector search SQLite extension. A little bit of background on what vector search is, if you haven't gotten a chance to play around with it. It's gotten very popular in the last year or two because of the AI craze and all that. So vectors are just from if you took these classes in college, which I did and I failed them, about vectors. Vectors are just a list of numbers. Embeddings are a specific representation of text that these embeddings models can generate. So these are these large machine learning models that we've trained. We give it a piece of text and it outputs a vector, but we call those an embeddings. It's a representation of text. It's still a fixed length floating point vector. So it could be it could have 1,000 dimensions. It's a at the end of the day, it's a mathematical vector of a list of numbers, but it is a representation of text. That's what embeddings are. And these embeddings allow you to perform calculations on text. So it's kind of like a calculator for words. That's kind of how I like to describe it. So you could answer questions like, if you have a bunch of documents and you have embeddings of those documents, where documents means any types of text, whether that's blog posts, chat messages, internal documentation for your company or whatever. You could do calculations like what documents are most semantically related to each other. if their embeddings are similar, meaning if those vectors are similar, where if it's cosine similarity between those vectors or their embeddings, that could possibly mean, based on these outputs of these embeddings models, that these documents are more closely related. Or you could answer questions like, what are the main groups of concepts in this data set? So you could do, a kind of a KNN nearest neighbor sort of thing, kind of partition a large textual data set that are all embedded individually. You could do like, oh, what are the 5 groups inside of this, right? Or, which documents are most likely to answer my questions? And we're able to do this because we change these text documents into embeddings, into these list of vectors where we could perform math on them, cosine distance, all that stuff. And that's the main benefit that we have for embeddings models. I won't talk a little bit about like how these vectors or embeddings are made, although these are 2 resources that I highly recommend if you want to dig deeper into like the math and the kind of the real world applications of embeddings. First one, What Are Embeddings, is a PDF by Vicky Boykis, who's actually at Mozilla now. It goes deep into the actual like math and implementation behind embeddings and kind of how they work and how these models are trained. And I also recommend Simon Willison. He has this tech talk called Embeddings: What Are They and what they are and why they matter. It's around 38 minutes long. Kind of goes more into the real world use cases that we have for embeddings. So yeah, both of those resources I definitely recommend to check out if you want to learn more about embeddings. And remember, these embeddings are created by embeddings models. These are machine learning models that were trained on large corpuses of text, very similar to large language models, although I would say that large language models are a little bit different, right? Large language models, first off, they're way bigger. The very good large language models are like hundreds of gigabytes, very hard to run yourself. If you have a GPU, it's much easier to run, but it's a little bit complicated to run LLMs, right? But embeddings models are much smaller. They're very easy to run yourself. The good ones, quote unquote, are like maybe a gigabyte. So that really fits into memory on most computers. You don't have to have a GPU to run an embeddings model. And there's a lot of companies out there that try to sell you on their embeddings model. Like OpenAI has one, Nomic, Gina. Like there's a ton of different companies out there trying to sell you embeddings models. But I just want you to know that you could run them yourself. If the embeddings model is open source, if it has an Apache 2 license, or MIT or whatever, you can run these embeddings models yourself and save yourself some cash. It is not like a large language model where the ones that you could run yourself are like not that great. You kind of have to like, do these quantized models and stuff to kind of get like okay performance. These embeddings models are very easy to run yourself. It's not resource intensive. It's fairly easy given some of these new libraries that are out there. For example, transformers.js, you can run embeddings models in your browser. So you don't even need to install anything. You just visit a website, run it yourself, runs in your browser. It might be a little bit slow, but it works, right? So these embeddings models, there's a lot of different ones you could choose from. My favorite that are free, that are good for at least English use cases, are the 3 that I listed here: Snowflake, Mixed-Bread, and Nomic. All 3 companies kind of train and release embeddings models at some regular cadence, and these are the 3 main ones that I use for my day-to-day. Specifically, the Mixed-Bread extra small one is a fairly new one that I really like. Again, it's mostly English-based, which kind of sucks, but there are other embeddings models that are multilingual. So, you can search for something in one language and get results back in another language. That's always cool. But definitely with the embeddings models, try to look for open source ones that are free. It can be very useful to you and save you a lot of money. But again, so we have embeddings. We embed our text with an embeddings model, and we want to store these embeddings. We want to store these vectors inside of some sort of database, right? A vector database, all it does is that it stores and queries a lot of vectors. Storage is a big thing with vectors. These vectors can seem small at first. So for example, a vector of a standard embeddings model, it might have 1,024 dimensions, right? A power of 2. 1,024 dimensions, where each dimension is a floating point number, so it's 4 bytes. 4 times 1,024, that's around 4 kilobytes of data for a single vector, right? And you might have hundreds of thousands or millions of these vectors. So if you have a million of those 1,024 dimensional floating point vectors, that's already 4 gigabytes of space that you need to like save to disk or manage, right? A lot of vector databases, they may store it into memory, and that can get kind of unwieldy. Like 4 gigabytes just for a million documents can be quite a lot. So that's one challenge that vector databases have to solve, like actually storing these vectors. And to query these vectors, the most common use case, the one that we're going to talk about the most in this presentation, is a KNN query. What that means is that, like, hey, I have a list of documents that I have embedded. They're all vectors. They're stored in my database. I have a query, like, maybe, for example, you have internal company documents that you are storing into your vector database, right? And they're, FAQs, onboarding, all that stuff. If you have a question about that, like, what is the paid time off policy that we have? What you want to do is you want to embed that query that you have, paid time off. You want to search it through all your internal company documents, and you want to get the 5 nearest articles that relate to do with paid time off, right? So that is the most common query that we're going to have, a KNN query, where you have a query that is a single vector, and you go and you search through all the different vectors you have inside your vector database and return the top 10 or top 20 closely related articles to kind of use that in your application to provide context or provide information, right? Just like a regular search result, but instead we're using vector search. So that's the main goal that we have for vector databases. There's a lot of different ones you could choose from. There's a lot of ones you could pay for that are closed source, like Pinecone and Vespa, and Cloudflare has a few. There's a few open source ones that you could kind of run yourself. These typically require a giant server that you have to run that will accept requests and store data and has its own little thing. Some pre-existing databases have their own vector search solution, so you don't have to install or manage a separate database service. For example, PG Vector for Postgres. Redis has its own little vector database thing. DuckDB has one as well. Or sqlite-vec. This is exactly where sqlite-vec happens. You already if you already use a SQLite database, or you can create a SQLite database for your application, and you install this extension inside of your SQLite database, and it stores it inside of there. It does everything. That's kind of where SQLite-vec falls in this list of from one end being paid as a service, closed source, to the other end being open source, run on your already running database. That's where sqlite-vec kind of goes into all these different vector database solutions. So what sqlite-vec is, it is a SQLite extension that does vector search, like we talked about. It uses custom SQL functions and virtual tables to do so. It works inside of any SQLite instance that you already have. So if you have a Python app that already uses SQLite to store database, it'll work there. If you have a Ruby application, Go, Rust, if you're using the SQLite command line interface, if you're using SQLite in WebAssembly, sqlite-vec will run in all those different environments in your pre-existing SQLite database instance. It is very similar to the FTS5 extension, or the full text search extension that SQLite offers. So it's very similar to create a virtual table, insert data, select data from it. Very similar to that approach if you ever tried that before. And one important thing about sqlite-vec is that it actually stores the vectors inside of your SQLite database. So it doesn't store them inside of a separate file or a separate server or whatever. It stores them within shadow tables inside of your SQLite database, which means all these different tools that work with SQLite, so all these backup tools, all these recovery tools, all these streaming replication services like Lightstream or LightFS or all those other ones, they all work with sqlite-vec. Because at the end of the day, all the vectors are stored within your database. So if you do a dump of your database at the end of the day to back up, or if you use Lightstream to constantly replicate your SQLite database into an S3 bucket, it will work with sqlite-vec will work inside of there because those vectors are already inside your database. You don't have to worry about managing a separate service. It just kind of all works. And as a quick demo of what sqlite-vec looks like, I have a notebook here that we can run. So the most common example that I show for sqlite-vec is has to do with news headlines, right? So a newspaper, they post dozens of articles a day. We could take those headlines that they post, embed them, and do kind of a small little semantic search demo with that. So that's what we're doing here. I'm using the New York Times, popular newspaper in the United States. They have a data set of all their news articles that they've had in the last 30 years that I have inside of this demo, and we'll take those headlines. It's a small, short piece of text, usually one sentence. We embed them, do vector search, KNN queries. Just an example of how sqlite-vec works. So that's what we have here. I have this little notebook that has this data set already pre-existed. I'll talk a little bit about this later, but here I'm using another SQLite extension called sqlite-lembed. And what lembed is, it is a SQLite extension that generates text embeddings. I guess one important thing about sqlite-vec is that it does not generate embeddings for you. There are so many services out there that already do this. So whether it's a third-party service or a Python package or whatever that will take text and generate an embedding for you, generate those vectors. There's a lot of different options for that, and sqlite-vec doesn't do that by itself. However, I do have other SQLite extensions that I will talk about later that will do this generating for you. So you provide it an embeddings model file, and in this case, sqlite-lembed is the one that we're using here. And this is this model right here. This is a file that is an embeddings model that we just load directly into sqlite-lembed, and we can use that to, as an example, we can call lembed on a piece of text like Alex Garcia, and it will return a blob. In this case, this is a do that. This is going to be a 384 dimensional vector because we're using mixed breadth's extra small embeddings model, which has 384 dimensions. This is an SQL function that sqlite-lembed offers, where you pass it in text and returns a vector of 384 dimensions. So what we can do as to show off what sqlite-vec is. So with sqlite-vec, you create a virtual table that stores vectors. In this case, we're creating vectors from the articles table. So I prefix it with vec_articles. We're using vec0. This is the vec0 virtual table implementation that we use. And this is the constructor to define the schema for your new vector table for using SQLite-vec. In this case, the vector that we have here is headline embedding. So we are embedding the headlines column. And that is going to be a floating point vector with 384 dimensions. We also define a primary key just to match it with the original table. We also define an auxiliary column. That's what that prefix is here for, that plus sign. This stores the headline text inside of a separate table. So that way we can do a fast lookup to kind of do metadata. So, after you get the 10 most related articles in our search, we want to see what the headlines actually are. So that's what the auxiliary column here is for. And we can define other metadata as well. So for example, news desk, that's going to be like if the sports desk of the New York Times posted this article, or the business desk, or so on and so forth. How many words are inside of each article, the published date of the article, that kind of stuff that we can all store inside of the vec0 virtual table for SQLite-vec. After we define the schema using this create virtual statement, we can just call insert into to insert data into this vector index using pure SQL. That's what we do here. So we have a base table already pre-existed inside the SQLite database. We insert all the metadata that we like. Here we call lembed to generate an embeddings from the raw headline text. We generate the embedding, it's a vector, insert it straight into the vector table, and then we're good to go. Here I just did 100 just to make it a little bit quicker, but you could do thousands or hundreds of thousands or even millions of vectors if you really wanted to. And after we have that, this is vec articles is just a regular table that we can query using SQL. For example, if I just want to get the top 10 or the first 10 rows inside of this table, we can see all the different columns here: article ID, the embeddings, the headline itself, all that other metadata is inside this table that we can query just with SQL. And if we want to do a KNN query, the real one that we want to talk about is a KNN query. So what we do here is we want to find the five closest related articles to our query, which is COVID. So five COVID related articles in this data set. We do that here with a regular SQL statement. We want to get we're selecting from the vec articles table that we just defined. Here is where we signal to SQLite-vec that we want to do a KNN query. So with the headline embeddings column, we want to do a KNN query. That's what this match means here. We want to match it against a vector that we provide. And this vector in this case is going to be an embeddings representation of our query COVID. So again, SQLite-lembed will generate a vector based off of our query here, and we want the 5 closest results. That's what k = 5 here. And we can see here that yes, after we get 5 closest results in this specific data set, has to do with like COVID-19 or pandemic or virus variant related articles. We can change this as well. So if I want to say like climate change, there may not be a lot of climate change articles in here, but we can also change that, and we get like I guess one important thing with vector search, it is not an exact search. It's just kind of like a fuzzy thing, like semantic meaning. So in this case, like there's not a lot of none of these articles say the word climate change in them, but they might have to do something with climate or with signs of the times, right? Or if I change this to politics, let's say, then I'll get political related articles like GOP or your Thursday briefing, all that stuff, right? So that is the main point behind SQLite-vec. It is pure SQL. So all the statements that we did here, the create table statement, insert into, select, that is using all pure SQL. We didn't have to do like some esoteric API to get to do those operations. They were just all available to us in SQLite-vec. So like I said, sqlite-vec, some of the nice things about it, some of the reasons why you might choose this is that it's pure SQL that we have. So no, you don't have to fiddle with like a Python specific API or a Node.js specific API. It is all SQL. It runs everywhere. And when I mean everywhere, I mean like every single operating system, Mac OS, Linux, Windows, Raspberry Pis. It compiles to all these different options, including mobile, whether it's Raspberry Pis or Android iOS. I have also packaged sqlite-vec across many different package managers. So for example, if you're using Python, you could pip install sqlite-vec, Ruby, gem install, Node.js, Rust, Go, there's a CGO version and a WebAssembly version if you don't want to use CGO. Dataset, there's a plugin for that. You could run dataset install to get it. SQLite utils, there's a which is a command line interface to run to work with SQLite databases that Simon Wilson created. There's also a plugin for that. It also works in WebAssembly. There's a demo version that you can npm install if you want to do it. So there's a lot of different ways to get started with SQLite-vec. Also, the entire source code for sqlite-vec is a single C file. It's like around 9,000 lines of C. If you want to take a look at what it looks like, feel free to take a look. It is a single C file just to make things easier to compile and cross-compile across many different platforms. That makes my life a lot easier. I'm also not the best C developer, so I just found it easier just to kind of, smooth brain, put it all in one file, not have to worry about includes or other weird like build systems. So it's one giant C file, makes it a lot easier to cross-compile or to run in different places. And if you're interested in like SQLite extensions or anything like that, feel free to use SQLite-vec as a reference to how to build virtual tables or SQL functions and all that. So that's one cool thing. Those are some of the main cool qualities of SQLite-vec compared to some other vector search solutions. Some cool features for SQLite-vec. You can there are a number of quantization techniques that you can use. So for example, a 32-bit floating point number is quite large. Like we said before, 1 million of them with 1,000 dimensions is around 4 gigabytes. So there's a lot of different strategies you could use to kind of compress these vectors. One of them is binary quantization. So what you do is you take the 1,024 dimensions per vector, and for every single one of those dimensions, if the number is greater than 0, you assign it as a 1, and if it's less than 0, you assign it a 0. And what that gives you is that instead of a 32-bit floating point vector, it gives you a bit vector. So instead of 32 bits, you store it all in 1 bit. So that is a 32x reduction in size. That is one way to save a lot of space. And instead of a cosine distance similarity, you instead use Hamming distance because you just have bit vectors. So Hamming distance, you just for the query and document, you just compare the zeros and ones, and if they match, it's a 1. If it doesn't, it's a 0. That is much faster. Doing that is much faster than doing a cosine distance similarity. And it's also less space. It is 32 times less space. So usually those queries run a lot faster. There is a performance hit that you get with it, so the quality of the search won't be as good when you use binary quantization, but some embeddings models are specifically trained on binary quantization loss, so the accuracy, you may not lose a lot of quality. For example, Mixed Bread, they claim that you preserve 96% accuracy after you perform binary quantization, so that's probably good enough for most use cases. And if you have a lot of vector, or you just got a lot of vectors, or you just want to make your vector search go faster, binary quantization is one approach to do that. As a quick demo of what that looks like using SQLite-vec, I have another notebook here, and we're going to do something very similar. We have the same data set. We're using SQLite-lembed to generate embeddings. What we do here is we have the same exact create virtual statement as we did before, but instead of a floating point vector, here I just replace float with bit. And what this tells SQLite-vec is that, hey, this vector is going to be a binary vector with 384 dimensions. So we can create it like so. Oh, let me drop the previous drop table vec articles BQ. So that way I can recreate it from scratch. And what we do is when we insert the vectors, we have this function called vec quantize binary. And what that does, it takes this 32-bit, it takes this floating point vector that we had before, and we perform binary quantization on that vector. So just like before, we take the 384 dimensions that are returned from SQLite-lembed. We take those and we attach a 1 on every single dimension. It's a 1 if it's greater than 0, or if it's less than 0, it gives it a 0. That gives us a compact binary vector that we can insert directly into the vec articles table using binary quantization. And when we perform a KNN search, the distance here, instead of a cosine distance, which is typically between 0 and 1, instead we get a Hamming distance. So this is the number of specific binary elements that match, right? So the distance is now going to be like in the hundreds because, there's 384 dimensions, so this is the most closely related one. So sqlite-vec knows when you use binary quantization to use Hamming distance over cosine distance because it's a binary vector instead of a floating point vector. That's one approach you could use to compress your vectors, kind of make things move a little bit faster. As shown here. There's also scalar quantization that sqlite-vec somewhat supports now. So what you do is instead of a 32-bit floating point number, you compress it into a integer 8, integer 16, floating point 16. So you kind of perform a scalar transform on that vector into a small embedding space. Again, you lose some quality, although it's most of the time not really noticeable. It's around 80 to 70%, which sqlite-vec offers. There's also a technique called Matryoshka embeddings. This is a little bit harder to explain, but basically, if you have a 1024 dimensional vector, if you chop off half of it before, you could expect to lose half of the quality if you chopped off like the last 512 elements, right? And you only kept the first one. And a 50% reduction in quality isn't that great. You could definitely notice it, so it's like not the best. But now what Matryoshka embeddings do is that these embeddings models can be trained on a specific loss function that keeps the context in the first few elements. So now, if you chop off the last half of the elements, if the embeddings model was trained on Matryoshka loss, if you chop off half before, you could expect to lose 50% quality. But now, using this new method, you could sometimes retain around like 95% quality. It requires support in the embeddings model itself, but if it does, that is one other way to kind of compress your vectors, use less space, and sqlite-vec does support it. For example, here's in this case, the Matryoshka transform happens down here in the where clause. So what you do is we're taking embeddings of this query called climate change. We're taking the first 256 elements inside of here, and we're normalizing the vector using vec normalize. So it's just a few SQL statements you could use on Matryoshka embeddings to kind of reduce the overall footprint of your vector index. That is another way that sqlite-vec supports compression. A few other features of sqlite-vec that I want to go through. Hybrid search. So one downside to vector search is that it's not always an exact match. One classic example that I like to use is in this real world use case. This person on Twitter, they use HBO Max, which is a new streaming service that's available in the United States. A year ago, they searched up Adventure Time, which is a popular TV show, popular cartoon TV show. But they had once they searched for this TV show on this streaming service, it was 32 results that they had to scroll through until they got to the show Adventure Time. Even though they searched for the exact phrase Adventure Time, there was still 30 other shows that appeared before the one they actually wanted, which was the exact same title match. And I think this happened because HBO Max at the time was probably prioritizing vector search over full text search. So the query Adventure Time is fairly broad, right? That could be anything from like, a show about like a show about Rick and Morty where it's like interdimensional adventures. It could be about like all these other different types of shows, but didn't match the exact term that we wanted. And if we wanted that exact term, that'd be full text search over vector search, right? For full text search, we'll give you just search Adventure Time and it'll return those exact tokens Adventure Time. Whereas vector search is more fuzzy. It's more about semantic meaning. It's more about there's a lot more that goes into it than just full text search. So hybrid search is an approach where you combine both results coming from a full text search and vector search, which you could do with sqlite-vec. You have a few different approaches to combine those results to kind of get better quality in your search engine. This blog post that I have kind of details how you can do that using sqlite-vec. So what we do in this example is that we create a full text search index using SQLite. There's a built-in FTS5 extension that I really love, and that works very, very well for full text search. That's keyword exact searches. So what you do is you create that using a create virtual statement, very similar to SQLite-vec. You configure SQLite-vec in the same exact way that I showed before. So create virtual table using vec0. And what you do is you have one giant, this query is the one. You have one giant SQL query that uses CTEs to kind of make things more manageable. You perform vector search in one step of the CTE. you perform full text search in another step, and then you have a final step in this CTE where you kind of combine both results depending on what score and rank they have. And what that gives you, in this case, we are searching for, I believe the search term is abortion ban. So again, this is searching an article, a corpus of news headlines. Our query is abortion ban, and we could see that in the results that are given, it kind of interleaves the vector results and full text results together using this reciprocal ranked fusion, which is one of the many different algorithms you could use to combine vector search and full text search results. So we can see here the top results are results that appeared both in the vector search results and the full text search results. So these are ranked higher compared to the other ones. So these first two results, they both appeared in the vector results and full text search results, which you could tell by the rank value here. And the other ones weren't, but they're kind of like interleaved together, right? So the third result, it appeared in the full text results, but not in the vector results. The fourth result was in the vector, but not the full text. So it kind of like interleaves the rest of them together. This gives you both the quality of, this gives you like exact search from full text results, and as well as like kind of like the fuzzy search from sqlite-vec. So that's one of the many different ways you can combine full text search and vector search using SQLite-vec. Which I recommend for most AI applications. If you're going to use vector search, you probably also want to have some form of FTS5 or BM25 results as well. Another one last feature that SQLite-vec has is metadata filtering. So this is one thing that I showed before. You can define using SQLite-vec. Let's go back here. You could define other columns on the virtual table and add additional filters on top of that. So for example, using this create virtual statement, if you want to have a filter like, oh, I only want to see articles that were published by the sports desk, right? Or I only want to see articles published by the business desk, or ones that have more than 500 words but less than 1,000 words, or published between this date range. You could apply those using different where clauses inside of SQLite-vec. So in this case, in this example, if you want the 8 closest articles that were published by the Metro News Desk that are less than 1,000 words, that was published between these two dates, you could do that using SQLite-vec, using purely from the where clause, which I find a little bit easier than some of the other vector database solutions out there, which require some complex JSON object where you have filters inside of an object where you define the column of the operation. It's a little bit awkward, but I find SQLite I find SQL much easier to apply, because you just have to add a different where clause to it. So SQLite-vec does offer that with metadata filtering. Oh, whoopsie. Cool. I'm going to skip over SQLite LEmbed and SQLite REmbed. So one thing that I want to get to is SQLite extensions in general. SQLite-vec is great. It is written in C, although you can write SQLite extensions in other languages as well. So if you're someone who likes Go or Rust or even Zig, it is possible to write SQLite extensions to do so. With SQLite extensions, you can create custom SQL functions, whether that's scalar, aggregate, window functions, or collations. That's possible to do using a SQLite extension. If you have a SQLite extension, you could do virtual file systems. So if you're someone who wants to build a SQLite database on top of S3 objects or on other like esoteric data storage systems, that's possible as well using SQLite extensions, using by building a custom virtual file system. Or virtual tables. Virtual tables are what powers SQLite-vec. That is what the vec0 constructor is that we showed before. That is, in my opinion, the most powerful thing you do with SQLite extensions. You can kind of abstract away data access to different places using pure SQL, right? A few things that SQLite extensions cannot do, if you're curious, that like some other databases can offer with their extensions. For example, Postgres or MySQL. SQLite extensions cannot add new custom types because SQLite doesn't really have types. So if you wanted to have like a custom vector type or a custom GIS type, you could store those as blobs in a regular SQLite column, but you can't have like you can't create like a new strongly typed type, if that makes sense. You also can't build custom indexes, which is one downside to SQLite-vec. You could imagine a world where you create a custom index that takes in a vector column and has an internal index representation for it. But that's not possible through SQLite, so we have to build a virtual table like we had before, very similar to what the FTS5 extension does. That is one difference to SQLite-vec to compare to, let's say, the libsql version of the libsql vector solution. libsql, they have their own vector search implementation that's very similar. It's built into SQLite, or at least their fork of SQLite, but it is not. But they were able to do that because they forked SQLite, so they can add an internal types, they could add internal index representations because they have access to just change SQLite in general. Whereas I worked more so in the whereas SQLite-vec works on pre-existing SQLite databases, so it doesn't have access to the internal database structure like libsql does. Oh, one question. So right now, SQLite-vec is purely brute force. So this kind of goes into the weed of what vector search is. But right now, SQLite-vec, when you do a KNN query, it will brute force search through all the different vectors inside of your database, which is slow after a certain point. I would say SQLite-vec is fast enough for like tens of thousands or maybe hundreds of thousands of vectors before it starts to really slow down. And by slow down, I mean like it takes more than 250 milliseconds to do that query. So latency is typically a big deal for brute force. I am working on adding an ANN index, whether that's diskANN or HNSW or something similar to that. I am working on bringing that to SQLite-vec. But for now, like SQLite-vec is pretty good for most SQLite use cases. Typically, you don't have like a lot of data in SQLite to begin with because it's usually local data that you have like on your machine or on your device, as opposed to like a very large database powering like, hundreds of thousands of users. SQLite does offer partition keys, so you could partition a vector index on specific IDs or values. So for example, if you wanted one vector index per user or one vector index per collection of documents, you could do that. And in that case, it won't search through all the vectors. It will only search through that specific partition key or that specific user or that specific group of documents. So there are ways to kind of help with that brute force slowdown, including quantization like binary quantization or Matryoshka embeddings, or a few other different approaches you could take to kind of make things a little bit faster. But that is one limiting factor for SQLite-vec. That is, it is only brute force now, although an ANN index will come at some point. One thing about SQLite extensions is that I really like them. I love building them. I've done them in many different languages, just depending on, first off, what language I know, what language I want to play with. But also like what makes sense for the specific problem that I'm trying to solve. Here's a list of them that I've built in the past. The ones with the blue dots, they're written in Go. The ones in the yellow dots are written in C, and the ones in red are written in Rust. So you can tell that like the ones that are written in C, those are usually fairly simple, or I use like a third-party library to do so. So for example, SQLite URL uses curl. They have a URL parsing library that I use to do there. So they're fairly simple because it is very hard to do complex things in C. Whereas the ones in Rust, those are a little bit more complex because I can use a third-party library to do so, right? So like, for example, SQLite regex, that uses the regex crate that Rust has. I didn't want to build one of my own. I didn't want to deal with like memory issues for other ones in C. So you kind of, I got to pick and choose what language solved the problem the best using all these different, all these different extensions. So feel free to look at the source code for all these if you'd like. I would say that SQLite extensions are very powerful. You should really look into building one. Or if you want to build a database, try to build a SQLite extension first. Because another nice thing about SQLite extensions is that it solves all the hard problems with databases. I didn't set out when I was building SQLite-vec, I didn't want to go build a vector database because like I don't want to deal with like managing data or like fsync or transactions or making these safe or all these other problems that come with data storage. But SQLite-vec already solved that, right? So if I can already use SQLite, which has one of the most verbose and powerful database implementations out there, if I could just use that pre-existing and just add a few nice SQL things on top of it using SQLite extensions, that is much easier to me than trying to build my own thing. So SQLite extensions, very great for this kind of stuff. Virtual tables. So one thing that I'll do is I will go over what the Vec0 virtual table is code-wise if you just want to learn how virtual tables work. I guess one quick overview of what virtual tables are. Most regular tables in SQLite are built into SQLite, right? They're B tree based, so they're stored in the file system. within different pages inside of the SQLite database file that is managed by SQLite, right? Like a regular table is stored in a B tree inside of the SQLite database file. What virtual tables offer you is that a virtual table will allow you to store data anywhere. And what they basically are, when it comes down to it, looking at the code, it is basically a series of callbacks that SQLite that you provide to SQLite that SQLite will call when you query a SQLite database. So whenever you insert into a virtual table, you get a callback in C or Rust or whatever that you define that allows you to figure out where this data is sourced from, right? So SQLite will, when a virtual table is created, it gives you a callback saying, hey, here are the arguments. Is this a valid table? When it queries your database, when it'll say like, hey, this person queried your table with these columns, with these where constraints, with this order by, with all these different options, give me the data for every single row in the resulting query, right? So you can source this data from anywhere. It could be from virtual tables. You can create a virtual table implementation that reads data from a CSV. You can hit an HTTP endpoint. Another database. You can do whatever in these virtual tables as long as you define these callbacks in the correct way. They don't have to be stored within this. The data itself doesn't have to be stored inside of a SQLite database, although it could. That's what I do for SQLite-vec, just to kind of keep things transactionally safe. But if you wanted to, you can have a virtual table that queries a Google Sheet and returns data using SQL, right? Or it can query a Postgres database or a Notion table, or all these other different places. Virtual tables just allow you to query data from anywhere using pure SQL, which is quite nice. So what I'm going to do is I'm going to go over what this looks like for SQLite-vec, like given the SQL, kind of like what C functions are called using the virtual table implementation, and kind of like how that works. I would say that if you really wanted to, the virtual table, this page inside of the SQLite documentation goes very, very deep into how you can build a virtual table and what all the different methods mean. It is a fairly long document. It honestly took me about like a year and a half to really understand like everything that has to do with this. But that is one way to like kind of really, so that's one way if you to learn about how virtual tables work and all that. Or I'll just go over like step by step what it means for SQLite-vec. So when you define a virtual table for SQLite, you basically provide a bunch of callbacks in C. So that's what this is right here. So we have the vec0 module, which SQLite-vec defines, and all these functions right here, the vec0 create, vec0 connect, vec0 best index, these are all functions that SQLite will call, kind of like callbacks, right? And each of these functions have its own specific purpose. These are all the ones that SQLite-vec has defined. As you can see, there's a few of them are to-do options. So for example, X rename, I just haven't provided yet. That's a callback that SQLite will call whenever there's an alter table rename statement. So if someone wants to rename their virtual table, they could do that. I haven't implemented that yet. And a few of these like release and save point and all that, like those are transactional related. That's something that I haven't implemented for SQLite-vec yet. And you, in C at least, you take this module, you provide it to SQLite. SQLite will take that in and be okay. So whenever someone calls, for example, whenever someone calls a virtual table statement using vec0, so using the module that you defined, SQLite will take the callbacks that you gave in the beginning, and it will call them and be like, hey, this happened. Tell me what to do for this table. So in this case, whenever this SQL is called on the left-hand side, the create virtual table vec articles, SQLite will call the xCreate method that you provided saying, hey, this person called the constructor with these string arguments. So they called, in this case, there's going to be 1, 2, 3, 4, 5, 6. So SQLite will provide an array with 6 string elements saying like, hey, someone wants to create a table with these columns. Is this a valid table? So what SQLite-vec does is that it will parse through all these different column definitions. So it'll parse through article ID, integer, primary key. It'll parse that, make sure it's correct. It'll make sure that, at least for SQLite-vec, it'll make sure that at least one vector column was created. So in this case, this is the headline embeddings column. It will parse through all the different metadata columns that are also a part of this. And it will say at the very end, it'll be like, hey, yeah, this is a correct table. And you're okay to query it. And it also tells you what the schema is. So in this case, for SQLite-vec, whenever this method is called, whenever xCreate is called, it creates all of these shadow tables within your SQLite database. I won't go into like what all these shadow tables mean because it kind of goes into the weeds of things. I will likely write a blog post about how sqlite-vec works and what all these internal shadow tables actually do and how they're all connected. But this is what these are the shadow tables that SQLite-vec creates and stores data within your SQLite database. So it will like after xcreate is called, it will say like, yeah, like this is a valid table. Here's the schema. Like, so here are all the columns in the schema that are needed to query this table. Go ahead and send me like other statements for this table, right? So this is one example of how like the underlying C API works. So after that's created, then we could like do insert into statements, right? So in this case, on the left-hand side, we have an SQL statement that is inserting data into the virtual table that we defined. So in this case, it's just an insert statement. We have three rows that we are inserting. So we're providing the article ID, the vector, the embeddings, the vector embedding, the headline, all the different metadata columns that we have. So what SQLite does is that whenever someone inserts into our table, it goes, hey, first off, I'm going to call your xBegin method, which starts a transaction, a read-only transaction, and then it calls xUpdate. xUpdate is a general C API or C callback that says like some sort of update is happening on your SQLite database. This happens on inserts, deletes, and updates to your virtual table, and there's some internal logic you can do to determine if this xUpdate call has to do with an insert, delete, or an update, and it calls it once per inserted row. So on the one on the left-hand side, it will call xUpdate 3 times with the provided data as an array of values, right? So it's an array of values, 1 per column. And what you have to do is that you take this array and you're like, okay, first you have to like validate all the data that was provided. So in SQLite-vec's case, it'll do some validation like, is this primary key unique? Is there any like unique constraints for this primary key that we have to worry about? So someone doesn't insert the same row with like the same ID like 4 times, right? Then internally, SQLite-vec will do a few things like it'll find the next available chunk position, which is an internal representation that SQLite-vec uses to store data. It will write vector data and it'll write the metadata that is provided into the specific shadow tables that it cares about. And then it will do some like internal indexing with this provided value. And then if that's good, it returns, yes, that update was good. Go ahead and return all good to the user to SQLite. And then SQLite will take that. And once the transaction is complete, it will call xsync and xcommit. You could use these as transactional hooks. If, for example, if you had a virtual table that stores, for example, it will proxy the data into a Postgres table, right? So you insert data into your virtual table, and you on your own hand will take that data and like enter into a Postgres table. You could use xsync and xcommit as like a transactional thing, right? So when you call xbegin, you start a transaction on your Postgres database. Xsync, then you sync that data, and xcommit, then that's a flag that like everything's done. So again, these are all callbacks that SQLite will call depending on what SQL is provided to your virtual table. So that's how an insert into works. So someone inserts into it, it does all this validation, it will commit those results inside and SQLite-vec will do this inside of your SQLite database, inside of shadow tables inside of there. And then one last query that we'll go into. When someone queries your virtual table, in this case on the left-hand side, we have a sample KNN query with metadata filters that we talked about before. So again, we have a KNN query because we're using the match keyword on the embeddings column that we have. In this case, we're getting the 10 mostly related articles to climate change published by the Climate Desk and whatever else. But what SQLite does is that when it receives a query like this to a virtual table, it will first call xBegin to say that like a transaction has started. It will call a function called xBestIndex, which is a callback that you provide. And what SQLite does in this case is that it will call this method multiple times. This is the query planner calling the SQLite query planner calling on your virtual table, being like, hey, can I query your table like this? Can I use these columns? Can I use these where clauses? Or like, it'll provide everything. So like every single where clause. So in here, like the k equals 10, the news desk, and in these array of values, it will call your SQLite virtual table implementation, and it will ask, how expensive will this query be? Or is this query even possible? So your virtual table implementation will take that and it will have to kind of guesstimate how expensive that query will be. And depending on what the SQLite query planner provides and what it wants to optimize for, it will take all those and it'll figure out the most efficient way to query your database, right? So every time x best index is called, which could be multiple times for a single query, you have to provide it a query plan. And at the very end of it, SQLite will take all those different options that it has and it'll be like, okay, I'm going to choose this query plan. So it will call X filter down here and be like, this is one query plan that you provided to me before. Go ahead and execute this query plan. In SQLite-vec's case, what it does is that inside of X best index, it will figure out like, okay, is this a full scan? Should I just return all the rows in this query? Is there a specific row that I'm looking for? So for example, if you want to look up a specific row ID, like, oh, I want row ID for user 123. That is another query plan that SQLite-vec discovers and outputs for depending on the query. Or is this a KNN query? Is there a match clause on an embeddings column that we can use? And did they provide a K value, whether it's K equals 10 or a limit 10 or whatever? And are there other like metadata filters on top of that? So it'll take all those and it will return a query plan saying like if it wants to do a full scan search, a point query, or one of these KNN searches. And what SQLite does is that it will choose which one is best and it'll be like, okay, so use this, I want you to execute this query plan. I'm going to loop and I'm going to call the XEOF or end of file method whenever I want these rows, right? So like once you've chosen a query, once you've executed it inside of xfilter, then I'm going to loop through all the different results using EOF, column, and next methods to basically say like, oh, are you done yet? Okay, you're not done. Give me column number 1 or column number 2. I want the value for that to provide to the user, and then give me the next one after that. And it's like, oh, are you done? It'll loop through being like, are you done giving me rows? If not, give me all the columns that I care about, and then proceed to the next one. Are you done? If not, give me all the columns that you want, and then go to the next one. So it's kind of like it's constantly calling these methods to provide the next row of results. Using these callback functions, SQLite is calling them to get the results, the row results back to provide back to the user. And at the very end, it will call xsync and xcommit to commit those results as a read-only transaction. So again, all these different methods, these are all SQL that these are all like SQL that SQLite parses, deals with, and provides callbacks for to your virtual table implementation, where you have full customizability to, apply different where clauses, apply different filters, make things faster. You have some option to tell the query planner which query plans to prefer over other ones. So there's quite a lot of like customizability you can do using virtual table implementations. And this is just one example for how SQLite-vec does it for some common operations you have for SQLite. And you can also imagine something very similar. So whenever someone drops a virtual table, there's a callback for that saying like, hey, someone dropped this table, go ahead and destroy everything that's needed for it. Or, oh, hey, someone wants to delete row ID 123, go ahead and delete that. So there's a bunch of different callbacks for all the different operations for a virtual table that you have full access to if you build a virtual table implementation on top of it. So yeah, I had a few other like project stuff that I could potentially talk about. I'll go through a few questions that I saw that I didn't get a chance to answer before. I guess in general, so I forgot to make an ending. Did I make an ending slide? I think I did. Yes, okay. So I could talk about this last thing embed file if I have a few minutes towards the end. But essentially, SQLite-vec, there is a dedicated channel to SQLite-vec inside of the Mozilla AI Discord if you are interested in that. Actually, let me get a link. I'll provide a link to that inside of this Discord server if you're interested in that. But also, like, so if you have any SQLite-vec related questions, I highly recommend that server and that channel specifically. I'll also hang around inside of this Discord and this group's Telegram as well. If you have any questions about SQLite-vec or virtual tables or whatever, more than happy to go really deep into it. I love this stuff. Also check out SQLite-vec on GitHub. Hopefully that is the correct link. Let's see if, yeah, that's the correct link. Let me just fix that. See right there. So yeah, so in general, if you have any questions about SQLite-vec, either this Discord or this Telegram or the Mozilla AI Discord, happy to answer questions there. A few questions that I saw over here that I want to answer just because we're running out of time. if I've considered product quantization in addition to binary quantization and scalar quantization. Yes, I just find product quantization a little bit difficult to implement, especially in pure C with no dependencies. I'm sure at some point I will do it, but though I will say product quantization, it sounds cool and it was very popular in the past, but I would say that like the quality of it, like the amount of compression that you get and the amount of training you have to do in order to make product quantization work well, compared to binary quantization, where binary quantization, it is very easy to implement. You just take all this, you just like for every single element, you check if it's 0 or 1 and you build a bit vector. That is a 32 times reduction using binary quantization. And if you choose the right embeddings model, the quality only goes down like 5%. That is a very good compression method that product quantization is hard to go up against, to be honest. For product quantization, it requires training. The compression doesn't really go down that much. You can maybe push it to 32 times, but like I'd say binary quantization is almost always better if you choose the embeddings model than product quantization. I'm sure I'll still add it at some point once I kind of figure out some other problems that sqlite-vec has relative to quantization. I'm sure it'll be included in sqlite-vec at some point, but I prefer binary quantization most of the time over other quantization methods, just because it's very easy to implement. The quality is like pretty good, and it doesn't require like training a new index or training a new quantization. A quantizer and all that. So that's one reason why I haven't provided a product quantization technique yet over binary quantization or scalar. A few other questions. The largest dimensionality of vectors I use with sqlite-vec. Currently, sqlite-vec, the limit is, at least for a vec0 virtual table, is 8,192 dimensions. It's like 2 to the power of 12 or whatever. I only did that just to avoid just so someone doesn't overload sqlite-vec, right? So I did add an artificial limit there. I could bump it up to like 16,000 or 32,000 if I really wanted to, and if you had the space for it, because that requires slightly more memory than the current implementation. But I would say most embeddings model. I believe OpenAI, the biggest one that I've seen that most people use is OpenAI's large embed model, which is 3,072 dimensions, I think. But to be honest, most of the time, like the more dimensions doesn't always mean more quality, and it usually means more headaches because that's just more storage you have to deal with and just slower queries. So most embedding models that I work with that are pretty good are like in the, at most 1,024 dimensions. Usually the really good ones are like 384 or 768, because that's just I think large dimensions doesn't mean always better, but I could always change sqlite-vec to add to handle more dimensions. I just haven't gone around to that yet. But that's just literally just a one line defined that I have to update to sqlite-vec just to bump that to something slightly higher. One question: can we customize normalization methods in sqlite-vec? Not currently. Right now, the vec normalize function just does an L2 normalization, I believe. I'm curious to hear what other normalization methods there are that could be useful. I'm happy to add more of them, to be honest. Just like happy to add more quantization methods. I've only done L2 compression because honestly, I just copy and pasted a C function that does it. That made my life a lot easier. So happy to include more normalization methods if need be. One question: sqlite-vec can work only with embeddings results. If you wanted to use multimodal via embeddings, yeah, you can use multimodal. You could do multimodal. So, for example, some embeddings models like Nomic, you can embed text using Nomic's text embeddings model, but they also have a vision model where you can embed images, and those embeddings are in the same space as their text embeddings. So what you could have is a database full of images, let's say like images that you're taking on your phone, and you could search with text. You could search through those images like dog or person or tree or whatever, and it will return results. It will do same KNN query vector search using the embedded text that you gave it, and it will search through the embedded images that you provided inside the database. And it will still work as normal. So it'll return images of dogs or return images of trees or whatever. So it is possible if you choose the right embeddings model. And sqlite-vec supports it just because sqlite-vec just stores vectors as is, right? It doesn't handle it doesn't do embeddings for you. As long as you provided the embeddings in the correct way, then it could definitely do multimodal stuff just fine. So whether that's using text to search through images or There are some other embeddings models out there where you can do like audio embeddings or face embeddings for like facial recognition and a bunch of other things. So yeah, that totally works with sqlite-vec because sqlite-vec only cares about you providing a vector and it's storing inside of the vector database. It doesn't really care about like where the vectors came from or anything. Yeah, if you want to, so for the custom normalization thing, if you want to create an issue inside of the sqlite-vec GitHub repository, go for it. And we can plan out, if you do want to raise a PR and all that, we can plan out what that looks like on that issue. Definitely include like what type of normalization techniques you want to see in SQLite-vec in addition to L2. And we can try to figure out what the correct SQL API could look like. But yeah, like if you have any feature requests or anything for SQLite-vec, check out the GitHub repository, see if there's an issue there. If it is, go ahead and give us a thumbs up or provide context about like why you want to see it. And more than happy to accept PRs if it ever makes sense. And if you want to like dig into the code a little bit more, just file an issue first so that way I kind of know what you're working on, so we don't like step on each other's toes or anything. More than happy to accept suggestions on new things to add or bug fixes or PRs or anything. More than happy for that. Yeah. Oh, I didn't touch too much about what the WebAssembly version looks like. Although if you take a look, let me go back here. So in the SQLite-vec documentation, I'll drop a link to this in the chat as well. There's a specific page on WebAssembly. Perfect. Let me drop a link to this in Discord. So in this case, the WebAssembly version of SQLite-vec that I offer here, what this does is that it takes the official SQLite WebAssembly package that they have started to distribute in the last year or so. It takes that same build and it just statically links SQLite-vec inside of that binary. So it uses the same API as like the official SQLite WASM build, mainly to run in the browser because that's what the official SQLite WASM build is meant for. So in this case, I have a demo of it on NPM, so you can copy and paste this HTML if you really want to. You initialize the database, and it's SQLite-vec is already built into it, so you can just call SQLite-vec functions in SQL and return results like that. That is one way to run WebAssembly with SQLite-vec. Another way that we have specifically for Go. So kind of go into the weeds here, but happy to talk more about it. So this guy, Nuno Cruces, I hope I said his name correctly. He has Go bindings for SQLite that doesn't use CGO, and instead it compiles SQLite into WebAssembly and includes a WebAssembly engine in Go to run SQLite. So it doesn't use CGO at all. It's all in WebAssembly. And SQLite-vec has a specific build that will provide that for you. So it's SQLite-vec compiled in WebAssembly in a way so that way it works inside of this specific Go library. So because in Go, sometimes you want to avoid CGO for cross-compiling reasons or performance reasons or whatever else. So that is another way that SQLite-vec has been compiled for WebAssembly to use in different locations. That's not just browser stuff. I've seen it also work in Flutter. I believe Flutter has some WebAssembly targets that SQLite-vec has been shown to like work in. I just haven't worked in Flutter much, so I don't really quite understand it. But yeah, it should work in other WebAssembly environments as well. Again, SQLite-vec is just a single C file. So if you already are building SQLite in some other esoteric platform, whether that's WASI or some other place, if SQLite-vec works there, literally you could just copy and paste the SQLite-vec like C file into whatever build that you have, and it should just work out of the box. There might be some flags you have to like to define here and there, but it should be possible. I haven't really tested much of like the WASI file IO performance yet. I know it's possible most of the time. Like whenever some new WebAssembly runtime or project comes up, they usually use SQLite as an example of how things work because SQLite is just a single C file. So it should be possible. Performance, I don't really know if that's a WebAssembly thing. To be honest, every time I look into WebAssembly, it's just kind of it's a little bit painful and I don't quite understand it. And the documentation is always a little bit iffy. But at least SQLite-vec will work there because SQLite-vec is just a single C file. It runs anywhere that SQLite can. So ideally it should work. There just might be some, a little bit weirdness here and there. So But more than happy if you have a specific WebAssembly platform that you're trying to target and you're having trouble getting sqlite-vec to work in that platform, feel free to file an issue. More than happy to work with you to get that to work. So yeah. All right. Any more questions from anyone? Again, I will be around. Let me drop a link to the slides again, so that way you all have it. Again, more than happy to answer any questions inside of this Discord if you have it later. I recorded a copy of this that I will post, I think, somewhere, and then and yeah, so we'll hang around in this Discord if you have any more questions, and feel free to check out the sqlite-vec channel inside of the Mozilla AI Discord that I will post in a little bit if you want to kind of talk more about embeddings and stuff. So yeah.
Hey, Alex. Thank you so much. I absolutely love this talk. I'm positive that everyone else also absolutely loved this talk. I think this comes close to the most.
Oh hell yeah, nice. For sure. God, I'm sorry. Yeah, yeah. Yeah, of course. Happy to be here. Love giving this talk. Don't care how early it is. Always love doing all this stuff. So yeah, again, I will hang out here inside of this Discord and inside of inside of your Telegram as well if you have any questions. And happy to chat more about anything. So yeah, uh, really enjoyed this. Thanks everyone. Really appreciate it. Yeah. Oh yeah, definitely. Hell yeah. For sure. You as well. Yeah. Yeah. For sure. Thank you. Appreciate it.